This is Meltdown, a demo of our recently launched integration between Google ADK and Temporal. Google ADK helps you build powerful agent logic. Temporal handles everything that breaks in production: crashes, retries, long running steps, human approvals, and distributed coordination. We're on the Las Vegas Strip. Ziggy's Ice Cream is a forward thinking ice cream shop that's using Google ADK to coordinate its growing delivery demands across the strip. And it's running on Temporal because ice cream can't wait when things go wrong. Orders are coming in from different hotels, and Ziggy's is ready to go. For each order, there are three agents that are working together for the delivery system's intelligence layer on the left. We have the fleet agent, the customer agent, and they're both running in parallel. They're answering different questions about the same order at the same time. The fleet agent is using tools to help it reason and recommend the best driver for an order, like calling the Google Maps API, and then checking driver positions and calculating ETAs for the closest candidates. The customer agent uses tools like Google Search to help find information about hotel events and evaluate the order priority and urgency. You can see those tools are listed on each agent card. Meanwhile, the dispatch agent is a sequential agent that's taking an input from both the customer and the fleet agent to make the final decision on which driver will get which order. Trucks are moving, orders are moving, things are moving about for Ziggy's delivery service. The drivers are the execution layer of these delivery orders. They batch pick up at Ziggy's, grabbing orders and delivering them to the hotels before heading back. At the top of the screen, you can see what the driver's status is. At the top of the screen, you can see the driver's status and the order status. Now let's look at the same system from the execution side, and specifically we'll look at the temporal UI to see what's happening. The order generation workflow is basically your workflow for simulating demand, producing orders from the hotels on a loop. Those orders get sent to the parent workflow, which is our Meltdown demo. The Meltdown runs the ADK agent team, manages assignments, and coordinates the drivers. Meanwhile, each driver has its own child workflow. It's managing its own batch of deliveries independently. That separation matters. It means one driver can fail without affecting the agents, and the agents can fail without stopping deliveries already in progress. So every LLM call, every tool invocation, every decision point shows up here as durable execution history. The fleet agent's ETA calls to Google Maps. Each one is a separate activity. So instead of one black box agent run, you get a system of individually recorded, individually retriable steps. In a complex system like this, things go wrong. A service loses connection, an API fails to respond, something else goes sideways. With Temporal, the system retains its state and picks up where it left off. You don't waste compute, you don't waste time, you don't waste tokens. Before I start breaking things, I want to show how this integration works in code. It starts here on the worker. The worker is the process that actually runs your code. When a workflow needs something executed, the worker picks it up and does it. The Google ADK plugin is registered here so that when a worker needs to call an LLM, the worker knows how to handle it. It's the bridge between ADK's runtime and Temporal's execution model. In the agent definition, the model is wrapped in temporal model. It doesn't change what model you're using, it changes how it gets called. And here's what it looks like under the hood. Every time the model is called to reason, it goes through execute activity, which wraps invoke model. Temporal catches this, makes it durable, retriable, and visible in workflow history. This is every time you're calling your LLM. And Activity Tool does the same thing for tools. Every time the agent calls an API to get data to reason on, like Google Maps for ETAs, that call is also wrapped as a temporal activity. So you get durability and visibility on both sides, the reasoning and the data gathering. Plugin wires it in. Model wrapper catches the thinking. Tool wrapper catches the data calls. ADK is defining your agent logic. Temporal becomes an execution foundation underneath. So that's how the integration works in code. Now let's see why it matters. There are three real production disruptions that we're going to demonstrate, and the system will just keep running through all of them. First off, we'll show you when an agent loses its tools. So let's break this fleet agent and basically disconnect it. You'll see in the UI that the fleet agent will go red to show that it's disconnected and offline, as well as the dispatch agent will signal that it no longer has access to this tool. But the system continues to keep running as though there's no issue. The new order is coming in. Fleet agent can't get the fleet status or route info, but Ziggy's system is continuing to keep going because the dispatch agent can degrade gracefully and it'll assign orders using the customer agent's data alone. It's degraded, but it's not broken. You can see this moment in Temporal. You can see the fleet agent's tool gets fleet status, activity, fail, get retried, fail again. Temporal retried it per the retry policy, then returned the error to dispatch, while the dispatch agent still made an assignment without it. Temporal handled the retry and the agent handled the adaptation. You can also see that those decisions it's making are degraded, and it identifies on the actual order when it's only using partial information to make that decision. So now we're going to reconnect this fleet agent. The orders that were assigned during the outage don't get reevaluated. They've already been delivered. It's basically a one-shot assignment. The pipeline just runs fresh per order as it arrives. Those degraded orders already were delivered, so now it will move on and start to look at the new orders that are coming into the system. And they'll get the full reasoning restored with these new orders that are coming into the pipeline. The whole time the workflow just kept moving. There was no restart, there was no redeploy, there was no lost state. Now, let's break a different part of Ziggy's system, not the reasoning layer, but the execution layer. Currently have a little driver on the road. They're going to lose connection. It happened mid-delivery, but this driver, driver A, is still continuing forward on its current leg. It was already on the road, so it already knows where it needs to go. But when it gets to its destination, it is not able to report back and say that it made its delivery. You'll notice that there's signals all across the UI that show you it's disconnected. Meanwhile, you can see that the rest of Ziggy's is continuing forward as if there's no issue. The child workflow isolation is basically working as expected. Each driver runs independently on its own workflow. So if you see this in the child workflow for A, how all the steps completed up until the point at which it started to navigate to Mandalay Bay, and then it lost that connection. And it continues to retry connecting, as you can see in that attempt next to the line item of driving. Now, when we reconnect it, the next retry will succeed, and the driver will go on about its business as if nothing had happened. It reports back that it made the delivery, and it'll move forward on its next destination. That's durable execution. No checkpoint hacks, no custom retry logic, no hand-built state machine. In our last scenario, we're going to show you when a customer changes their mind while an order is actually in mid-flight. So we'll see how this one order, the customer decides they want to cancel. And the cancellation request goes to the parent workflow first. And you'll see two wait conditions are playing out. We have a wait condition happening on the parent where they're waiting to find out what the actual decision is from the customer. As similarly, on the child workflow, you'll see that there's a wait condition also looking for the update, but this time specifically from the parent. You'll notice that the driver has still finished its leg and driven to the actual hotel and is waiting for that update. Meanwhile, the rest of Ziggy's system keeps running. Orders are still coming in, agents are still reasoning, and other drivers keep delivering. Only this one path is paused. Now, when we approve this cancellation, the driver skips the delivery entirely and moves on. There's no race condition. The delivery never happened. The change was resolved before it could start. And under the hood, basically, the parent approved it, signaled to the child with the decision, and the child's wait condition woke up and saw cancel. So two workflows coordinating via signals, both durable, both visible in the temporal UI. That's Ziggy's delivery system under stress. Google ADK handles the agent logic, composing, sequencing, tool calling, while Temporal handles what breaks in production, crashes, retries, long-running human decisions, and coordinating across workflows. With this integration, your agents don't just work on the happy path, they keep making progress when real systems fail. There are no checkpoint hacks, no custom state machines, no duct tape retries. It's just durable, production-ready agents. And with this, Ziggy's Ice Cream will be able to keep delivering successfully without any kind of issues along the way. Have a good conference, everybody.